Hello and welcome to this comprehensive motion tuning guide for the E6 HexMotion. This video will focus entirely on the driving mode, and in about 2 weeks' time, we'll have a separate video for flight mode as well. Now, this is not aimed only at our current customers, but also future potential customers who are interested in the customization capabilities of our platform and our software. And if you're interested in the product or a content creator, you can book a test session with us. We're based in Ingolstadt in Germany. I'll drop the link for the test sessions in the description. We can quickly switch over from triple monitors to VR and also have a center stick flight config as well if you're interested in trying that out. Now, this is going to be a bit of a long video as we'll discuss topics not only pertaining to our motion platform, but also discuss some aspects of vehicle dynamics and some misunderstandings of motion platforms in general. Now, one of the most important aspects of a motion platform, which is hardly ever discussed in reviews or product descriptions, is the center of rotation or a pivot point of a motion system. The most prevalent type of motion platforms on the market are these 3DOF systems with those 4 actuators, and they have the advantages of being super compact, affordable, and you can mount them to your rig. But they have a limitation, and that is that their rotation center is 20 to 30 centimeters below your hips. So now for suspension effects, this is all right, but for G-forces and load modeling, this is the exact opposite of what you want. Now I'll briefly explain what I mean by that. So when the rotation center is so far at the bottom, what happens is that you get this tossing effect, and during the transition phase, you get the exact opposite cue of what your body wants to feel. Let's say when you enter a braking zone, right? So the seat pushes you first forward and then brings you down into a lean down position. Now the lean forward position is the correct part, but in the transition phase, the fact that the seat is pushing into you is the exact opposite of what happens in a real car. Similar thing is for cornering, right? So even if you go for 2-3 degrees of cornering inclination, at the start, the seat pushes you into you from this side, and on the rest position, now you have a load from this side of the seat, right? And then when you have fast direction changes, you're sort of being tossed around as well. So this is what leads to this less is more philosophy, because you want to have those transitions as short as possible and reach those lean angles as quickly as possible as well. Now, this is not true for all 3DOF or 4DOF systems. There are motion platforms with decoupled actuators, so the actuators that have ball joints on top and bottom, and they usually have these pickup points where it's mounted to the moving platform on higher points. And this way, they already have a positive sway or surge built in, even though they don't have a dedicated access for it. In a typical 3DOF platform, the higher you sit in your seat, you're actually worsening the negative seat of the pants or the negative sway and surge cues you're getting. So even if you have a 3DOF platform at home, if you want to maximize the potential of your system, just lower everything down. Now, the best part about a 6DOF system is that we can place rotation centers anywhere we want. But not every 6DOF system can do this. To realize this, you need to have a 6DOF platform that has a lot of rotation range as well as translational range, so sway and surge. And this is exactly why we designed the system, and this is where it excels. And we also need a lot of peak translational velocity values so that we can hit those acceleration profiles for longer. Now, just a quick intro on what we try to do with motion and how our architecture works. So we have a super lightweight app on the PC side, where it takes about 0.5% CPU usage, and this runs at about 167 Hertz, also pulls the memory files of the games at 167 Hertz, but this is also limited by the refresh rate of the games themselves. And then we take this data and we send it to a motion platform that does all of its motion algorithms independently at 500 Hertz with the knowledge of where all the actuators are. This creates a very, very low latency, self-aware system. You need 6 basic data points. That is the longitudinal acceleration, lateral acceleration, yaw rate, pitch and roll, so where the suspension orientation is, and the heave acceleration or the vertical acceleration. And if these 6 data points are coming in with high fidelity, you don't need anything else. But we also take some other data points to do some predictions and miscellaneous effects as well. Now, what we do is that we take this data that's coming in and we divide it into 2 streams. Layer 1 is the G-force, and that is the highest priority of our system. And then layer 2 is the suspension effects or heave effects. But even though those effects come out really, really well, those layer 2 effects are sort of a second priority for our system. And once we take the data in, we have this control over here, which has these 2 knobs. So this knob controls layer 1, and then this knob controls layer 2. And we set these to max when we're doing the motion tuning. And then we have the option of reducing an effect if it gets a bit too much while we're driving in game. So let's say that this is my motion platform. This is the moving part, and this is where my hips are. So in layer 1, what we do is that we use separate rotation points, separate dynamic rotation points for longitudinal acceleration and lateral acceleration, and we place these rotation points in sort of a torso area, because the goal is that we want to take sort of the normalized traction circle and then map it to the limits of our system. Now, what I mean by the limits of our system is that we're trying to make sure that at any given time, on the limit of the attraction circle, 4 of our actuators are on their absolute limits. Now, motion platform has rotation limits of about 15 degrees in pitch and roll each side, so that's 30 degrees in total. But because we're also using a combination of sway and surge with these pitch and roll combinations, we can't use the entire 15 degrees. So we sort of reach a compromise where we set the rotation centers around here in around the torso area, and then we try to target 12-degree inclinations that give us nearly 0.2 Gs of lateral and longitudinal G-force. We can go higher, but we won't be able to hit those lean angles. And those lean angles get you that convincing G effect. Now you will see that if this is my rotation point, so my head will still be moving a little bit outwards when we go through corners. Right now the difference is about 20 to 25 centimeters. And when you compare this to a 3DOF system, that would be about 1 meter. So yeah, that's a huge difference in the amount of tossing effect you're getting. Then what we do is that once the high priority layer, which is layer 1, has taken this motion platform to, let's say, to its new position with this rotation point, we use the local rotation point over here, and then we map all our suspension effects over here. So for example, you hit a curb on the right. Now it's not going to use this rotation angle. It will go to this new position and use this rotation angle to mount the curb. Now, regarding rotations, it's really important that with these surge sway speeds and these rotation angles we're targeting, the displays always go on the motion platform and you are in a VR headset. It is one of the most immersion breaking things in sim racing to have the steering wheel moving about and the dashboard and horizon staying in one place. So we try to avoid this. And the question with the rotation, yes, in the first 5 to 10 minutes, your body does feel the fact that it's rotating, but somehow your body gets adjusted to it and starts to negate these effects. After a certain point, you only start feeling those planar G hits, and your body sort of ignores the rotation part that's happening. So that was a quick intro on how a motion platform works, and I'll try to get you more in-depth information in coming videos targeted on the kinematics and capabilities of our system. But now let's start with the setup side of things. So now we have our app open here, and you can download this from our website if you're interested in having a look. On top here I have the COM port. Right now I'm connected to the motion platform with COM port 3. And on the top here we have our telemetry tab. So the telemetry tab opens up this window. And this graph we're going to use to tune our G-forces even before we turn on the motion system. Then underneath we have our device panes, so these different panes. So right now we are at the first page, which is the device page. Then we have a page for G-forces and then the layer 2 effects. So I'm just going to stay on the device page for now. These are all the native games we support at the moment. We're working on iRacing, and then in the coming weeks we're going to increase the number of games dramatically that are natively supported by our motion app. But for the moment you can use Simhub Telemetry. So we have a really simple plugin for Simhub that you can just download from a website, activate in Simhub. You don't need the Simhub motion plugin for this. Just use the plugin that we have, and it's just going to port the data onto our app. Now we use only the global variables that Simhub uses, not any game specific variables that Simhub also has. And this way we can ensure that all of the games inside Simhub are compatible with our motion system as well. The only drawback is that since Simhub runs at 60 Hertz, we have about a 16.6 millisecond added latency to the system. And as you can see, we're running our app at about a 6 millisecond latency. So yeah, so you feel a little bit of that added latency as well. And the fact that the motion data is now coming at 60 Hertz also limits the amount of fidelity that you're getting in the motion. But you still get a very good experience. It's just that when we have games that are natively supported, we have a lot more motion fidelity. And then we have the option of saving and loading config files. Then we have our recognized game. So this is for Simhub. So when I go to Simhub Telemetry at the moment, it's going to say LMU. And that's the game that's actually running at the moment. Then we have a motion mode and drive. So this recognizes the game and then sets the motion to drive or flight mode, since they used separate code blocks in the motion. And then at the moment, I have no loaded config. Then we get to the system state. At the moment, you can say that the system is powered on and I have the emergency stop pressed. Right, so when the E-stop is pressed, the motion is going to ignore any input signal. And then underneath, we have our firmware version for the MCU, the motion control unit. And we have the firmware version for all 3 drives, as well as their running voltages. Then underneath, we have our motor loads. So we have 6 motors, and as you can see that all of those motors are sitting at about 20 to 30%. Just for reference, I'm 85 kgs, and I have about 35 kgs of hardware peripherals mounted on the motion rig. So this makes it about 120 kgs, and the allowable max payload is 190 kgs. So if you take a look at the current actual system load, which includes also the rig, which is about 23 kgs. So we're sitting at roughly 143 kgs. And if you compare this to the actual maximum system load, which is 213 kgs, so you can see that we're at roughly 67% of the total motion load. Right, and so if I place, let's say, three 32-inch monitors in front in my current setup, along with the frame, three lightweight 32-inch monitors would be about 25 kgs of weight, and that will increase the front load as well to about 30%, and we'll still have about 40 to 45 kgs of load that we can put on the system. But the idea is to have the most lightweight setup you can possibly have. VR is the best, because that way you have very less rotational inertia and a very nimble system. And when we load this up to about 190 kgs, you're going to see that these motor load values go up to about 45%. And we still need that 55 to 60% headroom so that the motors have enough room available to do all of the acceleration stuff that they need to do. Then underneath we have our VR motion compensation. I'm going to go over this in a totally different video since this is a bit irrelevant to our setup right now. Now let's get to layer 1, and I have all of these knobs set to 0. Now the way we're going to do about this is that we do, as I said, we're taking 6 inputs from the game, and we're going to work with all of these inputs individually. So that means that when we're working with longitudinal acceleration, we only drive and see how longitudinal acceleration feels, and we turn all of the other effects off. In our g-forces, we have our longitudinal g-forces, then our lateral g-forces, and there are these two sections. So the presets are how the motion is actually reproduced, and then we have these 4 or 5 options here in the middle. These are all the pre-processing we're doing on the PC side before sending things out to the motion. So we can individually set our scale for acceleration and braking. Then we have our aero compensation. This will be active in a future app update, so we don't have saturation, high-speed cornering forces, as well as maintain fidelity at low-speed corners as well. So the aero compensation is going to help us with that normalization. Then we have 2 types of smoothing. There's a constant smoothing. This is our standard alpha for the low-pass filter. And on top of that, we have a dynamic smoothing. So this dynamic smoothing is something I'm going to get into when we do the lateral g-forces. As you can see, we have a pitch scale and we have a roll scale. So what these are basically that when you each and every single preset, like N-curve 1 or COR 300, I'm just going to go over them, has its own target rotation angle, right? So in longitudinal g-forces, so the pitch is going to have either a 15-degree pitch down target or a 12-degree pitch down target, depending on what effect we're adding. And we can set the rotation scaling accordingly. We can also set this to 0 if we want to simulate only surge. And this does not have any effect on the internal motion algorithms. It's only just before we output the layer 1 data to the inverse kinematics. Then underneath we have our braking prediction strength. So the takeoff prediction, this is for flight. I'm not going to go over that at the moment. So the braking prediction has, at the moment, let's say is 10. So this means that what we basically do is we try to do a bit of a build-up. And this build-up helps our longitudinal g-force motion queuing. And so what we're going to do is that when the motion platform is moving forward, so 10 centimeters means that it will slowly build up to about a 10 centimeters of forward surge, giving us a huge slingshot at the back to perform the desired velocity profiles. And I'll get to that in a bit. In the longitudinal g-force, we have setups like N-curve 1, N-curve 2. I'm just going to go over N-curve 1 first. Then we have center of rotation. If you can see from that camera, the mathematical center of rotation of our system is at the height where these ball joints lie. And as you can see, it's about coinciding directly with my hip. And if I use CO center of rotation 300 or 400, 300 will approximately bring it to the center of my torso, and COR 400 will bring it over here where my mic is. The center of rotation is basically a coupled method in which the surge amount follows the rotation angle with this ratio that is the radius. And then we have COR 400 dynamic that I'm going to get to in a bit once I've explained N-curve 1. The N-curve 1 is a sort of a partly decoupled dynamic method between surge, acceleration, and pitch angle. And these are the two things that actually give you g-force. In translation, if you have constant velocity, or if you're just moving the system a certain amount in displacement, that will get you no g-force. G-forces or forces on the body actually come from acceleration only. And the end curve, what tries to do is dynamically control your acceleration and deceleration rates of the system. Before I turn that on, let me just quickly go through the scaling. So right now I'm in a GT3 car, and we have our telemetry tab open here, right? So I'm going to set this up to this, and as we're doing this at the moment, I will turn off all of the other effects. So I'll set everything else to 0 and also set the curve effects to 0. So the target is that when we start driving, we want to scale our longitudinal and lateral curves. So there's a little bit of a signal saturation on the graph output. By the way, since we're g-forces, I'll also do the lateral g's as well. Again, I have the motion off, and when I do braking, I have a little bit of a saturation on my longitudinal g-force signal, right? So we have a little bit of a saturation, and then we have a braking roll-off. So we're looking for a little bit of saturation so that we can have those peak angles and a more convincing g-loading effect. Again, this is about immersion. This is not about lap time. Motion systems don't get you lap time. So I'm going to do a cornering as well, and go through the lesmos. Again, you see that I'm getting a little bit of saturation on my lateral g-force as well. It's really nice, something that we're looking for. So this is sort of a good starting point. As you can see, we have a little bit of saturation on all of our signals on both our longitudinal G and lateral G signals. And let's get to turning on the motion. Now, before I turn on the motion, I'm going to set just to 0 as well. So this value is 120, and I'll just keep that in my mind. Yeah, starting with end curve 1. So now, as you can see, we're trying to find a compromise where we have a nice lean angle at the back as well. But at the start, I want the seat to hit me, to push me forwards instead of falling back, right? So I don't know if you noticed or not, but the end curve 1, what it tries to do is it creates an initial strong acceleration point and then sees how much available surge distance it has to do a very controlled deceleration. And I'm just going to show you in a bit of a comparison with the CR400 dynamic on what I mean by that. So end curve 1, CR400 and CR400 dynamic, all three of them have the same rear target. So 8 centimeters surge back with a 12-degree pitch down. So 12-degree pitch down is also 0.2 radians, is also 0.2 Gs. So roughly the amount of radian in inclination you have is also the amount of G forces that you're feeling. So when I go to CR400, now these fixed center of rotation method has absolutely zero braking prediction strength. So if I just do this, you can see that it's really responsive. But you can see, right? So because it does not have that prediction thing or move forward, it's using a fixed center of rotation, which is about this point, and this point basically. So on between me and the steering wheel, where the natural rotation point of the system is, the surge follows the rotational velocity profile of the rotation point as well. And in this case, if the rotational velocity profile is an acceleration, a constant rotation rate, and then a deceleration, the surge is going to follow the exact same method as well. And why this is important, so if I go to CR400 dynamic, now CR400 dynamic is a center of rotation method that uses the surge prediction as well. So when we move forward in surge, it takes the rotation point here from, let's say, 400 and puts it up to 600 till you get the surge back, and then it dynamically brings the rotation point down. So if I do this, you'll see that CO400 looks really responsive as compared to the end curves, but I'll show you what the actual fundamental difference is, and this difference becomes really apparent when you have visual isolation with like wraparound monitors or with a VR headset. So right, so as you can see, if you can see at the bottom right now, we're sort of moving out and we're building up surge. And if I do a break, so the CO400 dynamic is really responsive. It gets you a very good effect profile, but the fact that it follows the same velocity profile or tries to follow the same velocity profile of the rotation causes a bit of a problem that the end curve tries to solve. I will set my pitch scale to 0, and I'm going to show you the difference between CO400 dynamic with this build-up and with the end curve as well. So I hope that was a bit apparent, and if you want to go back and look at the video, you can see I'll quickly show you the sort of velocity, the rough sort of a velocity profile, what the end curves are trying to achieve and what the center of rotation method is trying to achieve. So the idea behind the end curve is that when, for example, we have, let's say, a 2G deceleration event in the game, it's going to be converted into 0.2 Gs automatically as it comes to the motion platform, because that's our target. And initially you're going to have a really nice 0.2 G acceleration till the end curve reaches its internal velocity limit for that profile. Now with end curve 1, we have a 390 millimeter surge velocity limit. With end curve 2, we have a 440 millimeter surge velocity limit. As you know, we have a maximum surge capacity of 530 millimeters per second at the moment, but since a lot of those resources are being used for the pitch down angle as well, we can't use that peak velocity. So what end curve 1 does, for example, is that when it does its acceleration up until 390 millimeters per second, now if you see 0.2 Gs is 2 meters per second squared. And if you do a really quick calculation, that we actually achieved this in about 0.2 seconds. So in this acceleration phase, we've traveled a distance of about 4.5 to 5 centimeters. Now, if we have only 4.5 to 5 centimeters or less travel that we have at the back, our motion platform is right now moving back at 390, 400 millimeters per second. So we're going to start decelerating the exact same amount and in the same braking zone, right? So we're still in the same braking zone. In a GT3 car, the braking zone is going to be about 1.5 to 2 seconds. And all of this is happening in 0.2 to max 0.6, 0.7 seconds. At the start of the braking zone, we're going to have a really nice, strong surge back effect. Then for the remaining time period, we're going to have an equally strong opposite surge forward effect, which is what you get in acceleration. And so when we do this surge prediction build up, and as I said that we have this target of 8 centimeter surge back, so we're giving the end curves a lot more distance at the back to have a much smoother deceleration phase. And if you go back and look at those comparisons that I just did with the CO400 dynamic and the end curve, you can see the difference between the two. Now I'm just going to quickly do end curve 2. So as compared to end curve 1, which has a pitch down target of 0.2 Gs, end curve 2 has a pitch down target of about 0.17 Gs and a 10 centimeter pushback. So it also has a much higher V limit. So it's a more surge oriented effect, and we're going to have a lot more of these end curves with different target values. Now, before I move on to the lateral G-forces, I want to show you what the drawback is with the surge prediction strength. When we do a lateral G-force simulation, it takes the motion platform to its absolute limits. Now, with corners that have flat out entries that don't have any braking zone or lift-off period, the surge prediction does actually not have enough time or an effect to mask that surge down effect. Even if you have a small braking or a lift-off period, you have a natural pushback, right? But when you enter a corner flat out and there's none of these effects, because the lateral g-force simulation is demanding that the motion platform comes back to its zero position, we're going to have a little bit of a disruptive event in which we have a surge back, even though there's no braking or liftoff event. Now we try to make this transition as smooth as possible, and I'm just going to quickly show you again what I mean by that. And for this, what I'm going to do is I'm going to set the cornering scale to 100, and I'll set this to COR 0. Basically, so if you do center of rotation 0 in longitudinal g-force and lateral g-force, then you're turning off the sway and surge to the system entirely. There's no other telemetry effect that's coming in that will utilize the sway or surge acceleration any other way. So what I'm basically right now trying to do is I'll turn this to 0, the roll scale to 0, and right now we are internally simulating a lean angle without having it come out to the system. And along with that, I'm going to leave the end curve to 1, and I'll set these to 0. So what you'll now see is only how the surge prediction works. And when I enter a flat out corner, so for example, we're going to do turn 3 at Monza. See, it starts to move forward. And then when I brake, the prediction dies down. And now when we exit this corner, so again, it starts to build up, and as you'll also see in the graph, when the lateral g-force comes in, so I'm moving in to this corner, and now because internally it's sort of simulating the lean angle, the surge prediction dies down, then it comes back up. Again, I've set my, as you can see, I've set all my acceleration and braking scale to 0. This is only the surge prediction part that works based on your brake and throttle position and the speed of the car. So that's how it basically decides if it wants to do a build up and do a surge back. Right, again now, if I just quickly turn into this corner without braking, this was probably the longest setup block, the longitudinal g-force. The remaining ones are going to be a bit shorter. We'll also temporarily switch to a Assetto Corsa for a little bit. So now we move on to the lateral g-force part, and as you can see, I've set my camera back there, so now you can view the sway and the yaw movements as well. And we're on Bahrain, but this has the section from turn 4 to turn 10, which is a very unpredictable sort of a section. And for motion platforms like ours that wants to focus on this traction circle part of the thing, I think this is the best litmus test. If I want to do only suspension effects, or have a motion platform that only does suspension effects or little rotations, this will be not a problem. So in lateral g-force, we have the end curve as well, but I would advise not to use the end curve. There will be an end curve dedicated to flight mode, and that is the only place where I would recommend using the end curve in lateral g-forces. Reason for that is that this individual decoupled swimming between the rotation and the translation works rather well in longitudinal g-forces, but when it comes to lateral g-forces, it creates a bit of a floaty effect, and I rather tend to switch to COR 400, the COR 300. Center of rotation 0 again is at my hips, so that's something I don't want. And then we have center of rotation 300. The center of rotation 300 has reaches the limits of the system by taking it to a 0.2 g lateral g-force and a 6 centimeter sideways sway. A center of rotation 400, on the other hand, has a higher rotation center, which would be somewhere over here, but has a lower rotation limit, so it goes to about 0.17 maximum Gs. To counter that, we have COR 400 to 300, and this is the effect that we'll be using now. So this uses a 400 millimeter pivot point at the center, and then transitions to a 300 millimeter when it moves outside. So in the middle, you have a bit more sway effect, but when you move out, we can also have the higher lean angles. So I'm just gonna do, again, I have all the other effects turned off. I have only the surge prediction turned on. Oh, I forgot to set the roll scale to max. So the roll scale is now max. Now we'll do a little bit of the high-speed section stuff as well. So that's turn 11 and turn 12. And I apologize a little bit for my driving since I'm looking at a window that's so small on the monitor in front of me. You can see that I think we still have a bit more room to turn up our scale of cornering. We're not saturating the limit a bit at the moment. I'm just going to turn this up a little bit. And you can see that now we have a little bit of a saturation, and I'll set these values up to what they were as well before, so we can have a full experience of only layer 1, and this is only G-forces. We're not focusing on any other road effects or curve effects at the moment. The important thing is here is that you'll see that I am in your frame while I'm talking to you. The top part of my body is not moving as much, and the camera at the back over there is actually going to capture how much my seat is moving and the correct seat of the pants cues that my hips are actually getting. So this is sort of a compromise that we set. In an ideal world, I would set the rotation center up here somewhere, but then I wouldn't be able to achieve the rotation angles that I want. The fact that because I'm not moving about as much on the upper part of my body as I would in a seat mover or a general 3DOF system, I can run these high rotation angles. My head and my torso are sort of in one place, so I can focus more on driving. Not right now, but when I have screens in front of me, I can focus a lot more on driving without being thrown off, basically. And that happens a lot in motion. When you're thrown off, it starts to become a very disruptive experience. And that's why people go for this less is more sort of setup. Now I'm just going to do a couple of corners with the entire layer 1 turned on. Now, just a quick sanity check. I'm going to set this up to COR 0, so you can see that how the motion behaves without having any higher rotation center. So the rotation center is now exactly where my hips are. But keep in mind that this rotation center is still 20 to 30 centimeters above the rotation center of what you would have in a typical 3DOF rig. I'm going to set these to 8 for now. And the reason is that I want to target the 0.2 Gs. These can actually go to 0.25. So As you can see, in those moments I had absolutely no seat of the pants effect. Because there's no negative surge involved, the radiation point is exactly where my hips are. So, but you saw the way I was being moved around, right? And that's something that we prevent when we take the rotation centers up and also add the correct seat of the pants effect. Now, one quick important note in layer 1, generally when it comes to hardware, we get this question a lot. You do not need a belt tensioner. You just need simple belts that are holding you in place at all times. These surge back effects and the pitch down angles actually create enough of a tug. It's not going to be as a strong tug as you get in a belt tensioner. At the moment, we're getting a lot more effects through our body while braking than you would generally get with the belt tensioner as well. And what a belt tensioner does is that it pulls you in, right? So it pulls this part of your body in, but also pulls you against the seat. And the entire purpose of our motion platform is to sort of create the correct cues and the interaction that your back has with your seat. So when we brake, the bodies actually move forward into the belts and away from the seat. Second thing is about your wheelbase strength. You don't need anything higher than 15 Newton meters. I've said this in a way that my constant cornering forces are in the range of between 10 to 13 Newton meters. Because what happens is that if, we're still talking about lateral G forces of not 2 Gs, but rather 0.2 Gs. And we have to sort of adjust all of our controls in a way that we can feel the motion. If I go with a brake pedal force of about 100 kgs, the braking effect of the surge is trying to pull us out. But if I tighten my core and I brake at 100 kgs, I'm pulling myself back so much that I will not feel that gut feeling that the surge back gives you. Similarly, if I have my steering wheel turned up about 18 to 19 Newton meters of constant steering force, I'm tightening my upper core so much that it sort of negates the lateral G-force effects that I'm feeling. It sort of ignores them. On the other hand, if we go down with the steering force strength really low, that also doesn't work because force feedback is still and will always be the primary feedback effect that we get from sim racing. So we need to find the right compromise, and 10 to 13 Newton meters is a really good sweet spot where you also feel a good amount of force feedback coming from the steering wheel while also feeling the lateral G push that we're getting from the lean angles. Now I've set my G-force effects all to 0. I'll also set the braking protection to 0 so that the motion platform doesn't move forward at all. And then now we can talk about yaw. So a lot of the motion platforms in the market throw the rear end out when you enter a turn. There's a reason why they're doing this. They're probably simulating cornering G-forces in a very limited way. This is a sort of effect that gives you a bit of rotation, but is quite unrealistic. So in our motion app, we have a yaw slip and a yaw dynamic. The yaw slip basically works in a sort of a similar way. It takes the average of the slip angle of the rear tires and then maps it to the motion system. I'm going to set this cutoff and this lat G suppression to 0. So basically what you can do is you can also control yaw slip with this yaw cutoff. This adds a bit of a dead zone, and then the lateral G for suppression. So this reduces the amount of yaw in the presence of some lateral Gs. Now I'm just going to do a couple of laps, right? So I have a bit of yaw. I'm not going to set it to 100% right now. So again, we go into the corner, and as you can see, I don't know if the rear camera is catching it, but we're sort of having these yaw moments. Just a quick moment. I'll set this up a bit higher so you can get a bit more of a pronounced effect at the back. Right, so as you can see, when I turn, the rear moves out. Now, is this realistic? No. Every race car goes through a certain yaw angle when it goes through a corner. Because if it does not have that yaw angle, the rear tires will not generate the slip angle that's required for the lateral g-force. But the way this actually happens is much different in real life than, throwing the rear part of the simulator out. And this sort of slip method creates a bit of an issue in our motion platform. So as we discussed earlier, so we're trying to pick up this rotation point, and we're trying to, so if it's a right turn, the motion platform is going to pull us in like this and then bring us to a rotation angle that's facing this way. The yaw is pushing us out from the back. So what effectively happens is that if my hips are over here, they become the rotation point, and the motion platform now moves out like this. And if my head is my index finger, it moves out this way. So it starts to do exactly the thing that we're trying to mitigate with the center of rotation method. If you use yaw slip, so yaw slip at the moment is only working for our native games, so for example for Course and LMU. But what I recommend doing is that you don't go with yaw slip, you actually use yaw dynamic. Now, what is yaw dynamic? And so if yaw dynamic is more than 0, then yaw slip will be ignored and it will switch to yaw dynamic by default. And yaw dynamic is also working with the telemetry that we're using from Simhub, so it's going to work with all of the games from Simhub as well. Now, the yaw dynamic is a method that uses the residual yaw rate to sort of distinguish the actual traction loss events. And I'm going to enhance this yaw suppression by using lateral G suppression. Lateral G suppression means that if I have, let's say, 2 Gs of force coming in, if I set this lateral G to 100%, what's going to happen is at 100% lateral Gs, so at 2 Gs that we're sending to the system, the yaw is going to go to 0. That's also something that we don't want. So we're trying to control the yaw in some cars as well at the limit of the traction circle. So I'm going to set this to about 30-40%. And I'll set the yaw cutoff, which is the dead zone, to 1. This is the default setting, by the way. So now when I start doing, I'm going to have a very, very low amount of yaw effect. If I do, so I'm going to do a couple of corners, and I'll try to make this really smooth because I'm in a car that has a planted rear end. So I'll try to make sure that no yaw comes in. Right, so as you can see, I'm turning into the corners, but nothing's happening. But I'll go over a curb right now. I'll try to hit a curb, and let's see if that catches a rear. Right, so that just captured a little bit of a yaw kick out. And now if I turn my traction control to 0, right, so on the same settings, right, so I'm trying to move this out. Now, because this is a residual yaw rate method, and we're back integrating the yaw position from the yaw rate, what you actually need to do is we have this thing here called center tightening. So center tightening does not actually affect the yaw slip and only affects yaw dynamic. And this is sort of a washout strength or a centering strength that negates that drift a little bit. So if you set this to really high, then it could be that, it's sort of a spring pulling the yaw back to 0. And if you turn this effect a bit too much, it might not even allow you to move out that much. So in a lot of other platforms, what happens is that when the yaw happens, the traction loss happens, and the motion sits at a specific yaw angle, the body's actually not feeling anything, right? Because now the motion platform is stationary, but in a new position. What we actually do is, so when we have lateral G forces, we tilt the yaw angle this way, and it moves the yaw now in such a way along this axis. So what happens is that all of the lateral G-force that you were feeling on the side of your seat sort of moves backward a little bit as soon as this yaw goes out. So it's going to be really good for drifting and rallying, because in those games you have a really high yaw angle, and the lateral G-force is actually not this way or exactly in this angle, but sort of is shifted back to this angle. So you're not just pulled back into this part of the seat, but sort of being pushed in as well. I'm going to try to do a controlled drift. I know it's not going to happen, but I'll just set this to COR 400 to 300. And because we're in an F1 car, I'm going to set the scaling to 80. So let's see how, if I can, do a little bit of the So now let's quickly talk about Heave. For Heave, what we do is that we take the vertical acceleration of the center of the car instead of using any suspension effects. And the reason for that is that it will sort of be counterintuitive if we map the suspension travel to the actual vertical motion of the motion platform. That would mean that if you're going through a bumpy track like Road America or Sebring Main Straight, you're driving a luxury car that has a higher suspension travel, is going to feel a lot more rough on the motion platform as compared to, let's say, a race car which has a very taut suspension and very minimal travel. I just have all of my effects now turned off, so yours turned off, and so the heave scale is what the output heave magnitude is, and so the heave smoothing is again the smoothing of the acceleration signal that we're sending in. And again, we're now working with an acceleration signal that we're trying to double integrate to get the position out of. And this means that we have a bit of drift. The heave acceleration in games does not only have drift, but the problem is that it also has a lot of pre-pitch from lateral and longitudinal g-forces because of the pitch and roll angles. So the center tightening is sort of the thing that, again, we used for yaw, and it's sort of a spring that sort of holds us down to zero. So now I'm going to go over this straight, and all of the effects are all turned off. This is only heave. Right, so you see that was quite bumpy, and now I'm just going to quickly switch over the car. So now I'm in the Porsche Cayenne, an SUV, and you'll see how much of a floaty drive it is as compared to the Formula 1 car that we were in. And if you want to increase the floatiness, so the amount that you can deviate, you can actually turn the center tightening down a little bit, so you'll have a bit more of a floaty effect. But we don't want to do that for layer 2, and I'm going to tell you why once we do the pitch roll as well. So now we're on the main straight again, and let's see how this compares. The settings are right now exactly the same. Right, so you see that it's still getting the bumps, but it's a much smoother profile. And if I view the suspension travel right now of this car compared to the Formula 1 car, then it's going to be the exact opposite of what we're feeling, right? So I'll turn this down to 0, and we'll jump back into the Formula 1 car because I want to do the pitch roll local effect with the setter cursor first, and then we'll move back over to LMU. So now we're back at Barcelona in the Formula 1 car. So I'll set this to 100. The pitch and roll is the local orientation of the car, and we have this divided into two sections. The local effect is what we're trying to model, and this is basically all of the pitch roll effects that we have in, let's say, a 50-meter radius of the car. And that means that if you're going uphill, you'll feel the uphill, you'll feel the motion platform go up. But if you're sitting uphill, the motion platform is going to come down to a 0 position. And how quickly that comes down to 0 is what we control with the washout strength. If you want that pitch up continuous, then you can add the global effect. And the global effect, you can set this up maximum to 50, but we leave that to 0. This is what's important. So we want to feel what the car is doing on the road locally, but not globally. Because if we have these global pitch and roll continuous effects, what we're doing is that we're taking away motion range from layer 1. And then layer 1 is going to struggle with the deceleration profiles that it has fit in. And all of the motion is going to be hitting either their bump stops and things that we generally don't want. And so we don't want this washout effect to be much high as well, because then the settling is going to be too fast and it will start settling in between effects. And so with setter cursor, you want to set this to about 50. With LMU, we set this to about 30. And I'm just going to drive a little bit, and working to see how the suspension effects actually come through. Right, so if I go over the I'll just turn down the smoothing a little bit more, so we have a bit more of a stronger, more direct feel. And even if I'm driving really slow and we're on a relatively smoother track, see in the back camera, but there's a really slight amount of movement that's going on in the actuators. Again, Heave is off for now, so now I'll try to hit the sausage grip so you can see that the car stays afloat a little bit. Ooh, it's a bit hard. And then, right, so you saw that for the time period that the car was in the air, the motion platform was also there. And now, one important thing is that somehow the curb effects, even though we're trying to pull this at a really high rate, the curb effects don't come out as well at high speeds. At lower speeds, they do come out quite well when we have the combination of Heave, but at high speeds, they're quite numb. And for this, we're going to have a bit more of an artificial effect. And as you can see here, we have these miscellaneous effects, and we have the gear effect strength. At the moment, the upshifting strength is really good. That's coming naturally through the longitudinal G-force signal. In the future, we're going to have a gear effect strength only for downshifting. Basically, the gear effect is a sort of a short thump in surge. So you feel only in downshifting that there's this additional thumping effect. And then we have these curb effect strength, which is at the moment only working in LMU, because LMU and R factor 2 have a tire flag for when the wheel is on a curb or a special surface. So we can just directly put that in. And right now I'm just going to quickly go to LMU to show you those effects. So now we're at Sebring in LMU in the BMW GT3. And I've set my yaw to 0, I've set Heave, pitch, everything to 0. And what we'll focus on is only our curb effects. So I'm going to set these to the strength to 5 or 6. And then you have the frequency adjustment below. So what happens is that we have a really simple sine wave that varies with the speed when you go over a curb. Right now it's a very simple effect, so it just adds Heave. Still quite immersive because even if a single tire goes onto that curb, it produces this effect. So if you want to increase the frequency multiplier, you can just add these to 7, 8. But the reason why I'm at Sebring is because I'm going to activate layer 2 to see all of the bumps. And Sebring has curbs that are mostly flat. So yeah, so let's see how this effect comes through. I'll set the force feedback at the moment to 0. So I'll go to controls, force feedback, and let's just put this to 0 for now. So I don't have any of those extra effects coming in. And I hope you can hear it with the mic, or it comes up in the motion, or it comes up in the camera. Right, so it's a nice haptic feedback that comes up to about 50 Hertz, I believe. That's the max that we've set at the moment. See that? I'm just going to go over the S's again. right? And now while we're at it, I'll also just quickly show you the gear shift effects. I'm going to put this up to 8, and it's a really short direct thump. I can't really tell how that came out on camera, but yeah, you'll have to come and try it out yourself. I'm just going to do 1 or 2 laps in Sebring to finish off the entire setup guide, and I'll go with all of the things that we set up. So we're going to go with Heave 10. These are really close to the default settings that we set, so we'll go with N curve 1, again to 120, and this was to 130. And we'll also add force feedback. So now we have all our effects. I'm gonna switch off the gear shift effect for now because I'm quite happy with the gear effect that's already coming. And I've set the yaw again down to its default setting, the heave, the pitch and roll effect, as well as the G-forces. So I'll just make one change over here. I think the heave tightening is a bit too strong, so the actual bump strength is not coming through that well, which you would expect on Sebring. So I'm deliberately going over these curves and stuff a little bit so you can see the responsiveness of the direction change. So thank you so much for watching. If you have purchased one of these platforms from us, thank you so much for your support and trust in this invention of ours. You are truly about to have a one-of-a-kind motion experience. And if you're interested in getting one of these, as I said before in the video, there's a link in the description. And until next time, till about 2 weeks when we do the flight mode for the E6 HexMotion. Thank you.